And welcome everybody to the Subnet Saturday. It's great to have you here. Oh my gosh, I have been running like a madman and tweaking a few things in my office, working on lights and trying to get things dialed in that way. And I'm so glad to have you here. I look forward to these live sessions every single week. We're currently doing 3, and we're going to focus on subnetting. Now, if you've been with us in the previous sessions on subnetting, on the IP addressing, that's a really important foundation for what we're about to cover today. So if you haven't already, if you're brand new to this channel, first of all, subscribe. Thank you for that. And go ahead and go through the playlist called the Subnet Saturday playlist. I think there's currently there's 5 or 6 videos in there as of right now, and it's growing. And these are just being added on top of that. So I wanted to talk with you today about how we can use our fingers, and I still use my fingers every single time I'm working with IP calculations and subnettings. And I want to share with you the secret as a base skill we can put in our tool belt, and then you can use it every time you need to subnet and get it right every single time. So let me go ahead and let me dial in my screens here for a moment. I also discovered that the light off this screen affects my lighting in this office. So I'm still dialing that in as well. All right. Let's imagine that we have this network to play with. And let me go ahead and bring up this tool right here. So we've got this network to play with, and we've been told by the boss, please set up IP addressing for this network. Maybe this is a remote office or a branch office. Let's call it a branch office. So we've been asked to set up this branch office. And here's a few things that we know right out of the gate. We know that if we have a router, that off of every interface on the router is a different network. So this would be network A, maybe between router 3 and router 4. This would be network B between router 2 and router 4. Between R1 and R2, that could be network C, and R1 and R3, that could be network D. And then we have these networks, that could be network E off of that interface, and E and F there. So how many is that? I guess I can just go around and count them there. 1, 2, 3, 4, 5, 6. 6 networks. So we have 6 logical networks, or 6 street names, that we would need to make this work in this current topology. So our boss tells us, you know what we want you to do is we want you to make it all work. And oh, by the way, we want all your IP addresses to use the address space of 10. Let's start easy. Let's go 10.0.0.0. And that with an 8-bit mask. So he says, you make this address space work. Or you know what? I'm going to take that off. Let's make it more realistic. Let's go ahead and carve out, and I won't put it over my picture either. Let's go ahead and say that for all this network, we want it to be 10.67.83.0 with a 24-bit mask. There we go. So we learned a little bit about masks on the way to this point in this journey. We know that an IP version 4 address, let me get the bigger camera here. We know an IP version 4 address has 4 parts. There are 4 different numbers separated by 3 periods. And those numbers are the 0 through 255. And part of that IP address is the network over here on this side, and part is the host over here on this side, and the dividing line is the mask. And so I'm going to assume, and I hope that everybody who's with me to this point has been through those previous videos and are comfortable that the IP address is 2 parts, the network portion and the host portion, and that the mask is what splits those, or is the dividing line between those two. All right, so having said that, if we are told by our management that we need to go ahead and set up this environment, and we are given one address space, 10.67.83.0 with a 24-bit mask, we need 6 networks. And that's a problem. That's a problem because we've been given one network. And so what we are going to do in this case is we are going to create custom subnetworks. Think of it like taking that address space of 10.67.83, and we're going to carve it up and make not just one big street called 10.67.83, but we're going to make several smaller streets out of it. It's sort of like if we had Elm Street, that way this huge street just is a mile or 2 long, and we've been told, you know what, that's not going to work. The city planner says you can't have a street in your design that is a mile long. Can you chop it up? So we say, yeah, and we can make little streets like Elm Court, an Elm Way, an Elm Avenue, an Elm Lane. You with me? We're just logically chopping them up into smaller streets, and then we might have different angles and stuff and put houses there. And we've taken one big street, instead of using a big street, we've chopped up into smaller pieces. And that's what we have to do here too with this network. is we take this address space of 1067.83.0 and with a 24-bit mask, and we would change it. And this is important. The way we're going to change it is we're going to change the dividing line between network and host. You might be thinking, well, Keith, if you have a 24-bit network, that means the first 24 bits, based on our previous discussions together, the first 24 bits is the street. So in this example, it's like 10.67.83, that's the street. And then the last octet, the last 8 bits are available for host addressing. Yes, that's currently how it is, but we're going to change the rules. We're going to take the mask, and I have one here. We're going to take this mask that's a separating line between the network and the host, and let's grab an IP address. There we go. So if the dividing line is currently here, so this IP address is 1042.77.238, and the mask is saying, oh, the dividing line's right here. All the bits on in the mask say, hey, these first 24 bits, they all represent the street or the network, and the last 8 bits of the host address, because the mask is zeros, it says, hey, those are all host bits. What we're going to do is we are going to steal additional bits that were host bits, and we're going to use them for creating additional subnets. Now, the purpose of today's discussion is to share with you a technique of identifying how many bits we need to take. So wait, let me put on a different hat for a second. All right. This is me. I've got a question hat. All right. You're saying that we take the traditional IP address with its mask, and what we're going to do, if we have a 24-bit mask, we are going to make that mask longer, maybe 26 bits or 27 bits or 28 bits, in order to create additional subnetworks. Spot on. That's exactly what we're going to do. We're simply going to take the mask we've been given, the starting point, and we're going to make the mask a little bit longer, by maybe 1 bit longer, maybe make a 24-bit mask a 25-bit mask, maybe make a 24-bit mask a 26-bit mask, maybe a 24-bit mask a 28-bit mask. Now, the reason we're doing this is so that we can create subnetworks, and we'll walk through that whole process. But my first and sole purpose here today in chatting with you is how many bits? How many bits above and beyond what we were given? So in this topology right here, we have 24 bits with this network right here. So the mask says the first 24 bits is the network, and we need to create additional subnetworks, so we need to start stealing. So the mask would look like this: 255, 255, 255.0, and in binary, that mask would look like I'm going to say first octet, second octet, third octet. They'd be all ones, right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so that's the mask, and then these would be zeros. So what that says is that the first 24 bits are the network over this way, and the host bits are over here. So all we're doing is we are going to start stealing from left to right host bits. So I don't know if you want to repeat after me or just imagine it, but the reality is we're going to have to steal some bits, host bits, bits that before we got there, before we started doing custom subnetting, those bits were being used for host addressing, and we are going to steal them. And we are going to steal them in a consecutive order from left to right. And so the question is, how many bits? How much longer do we need to make the mask? And how many bits do we need to steal and allocate towards network addressing to create custom subnets? And that's the discussion I want to play now with the finger game. So the finger game goes something like this. Let me get a marker as I go out of frame, but you can still hear me. Here we go. Now, I'm not encouraging you to do this if you're at work or if you're driving, or if you don't have some way to take this off of what we're about to do. I smashed my finger in the door a little while ago, so that's an owie. But anyway, I'm going to pretend our fingers are bits. Imagine our fingers are bits. And so you've got some over here and some over here. And if your fingers represent bits, the question is, how many bits do we need to go ahead and steal, take away from what used to be host bits, and allocate them as network bits for custom subnetting? And the secret to this is treat your fingers like bits. Let's do this. That probably won't come off for a while for me, so I don't recommend you do that. Oh, is it going to be backwards in the camera? Dang. So I may have the anyway, so bits. So hopefully that's right for you. Anyway, so our fingers represent bits. So having done that, on your thumb, your fingers and digits are representing bits. On your thumb, I'd like you to write a 2, or just imagine it. If you've got a good imagination, the imagination will do it for you. So I've got a 2 on my thumb right there, the number 2. So you might say, well, Keith, let me just rehearse what we've talked about so far. You've said that to create custom subnets, we're stealing bits that used to be assigned to host addressing, and by doing that, we're going to make the mask longer than when we got there. So if it's a 24-bit mask, we might be making a 26 or 27 or 28-bit mask, depending on how many bits we steal. That's exactly right. So in the finger game, our fingers represent bits, and to calculate how many bits we need to steal above and beyond what the default was that we were given, we're going to put our thumb up in the air, and we have a 2 on our thumb right there. And just look at that thumb. Now, if you don't want to mark up your thumb, I get that. I've taught, in fact, I think I taught this the first time at Cisco Live like 8 years ago. So I was thinking, what is a clever way that I can really have people get this idea about how many bits to steal for custom subnetting? And I came up with a finger game. Now, I think I came up with it. Sometimes I have ideas that, I think this is an original creation from like 8 years ago. Anyway, the idea is treat your fingers like bits, write a 2 or imagine a 2 on your thumb, and whenever you need to calculate how many bits you need to steal, you simply put your thumb up in the air and you're looking at your thumbnail, which has a 2 on it, and you say 2, because that first bit represents 2. So let's apply this, and then we'll go through the exercise. So in this topology here, we need 6 networks to support this. We've been given one network by the boss, 1067.83, with a 24-bit mask. To do custom subnetting, we are going to have to go longer for the mask. And the question is, how many bits? Now, if we took all the bits, if we took all the host bits and said, we want to use all those host bits for network, then you wouldn't have any bits left for the actual hosts to actually use. So we want to take enough bits and make the mask longer to make sure we can reach our network goals, but at the same time, we don't want to take excessive amount of bits. So let's imagine we need 6 networks. And the question is, how many bits do we need to steal to get that? And the answer is, you put up your thumb. Always put up your thumb and just say, oh, hey, there's a 2 on my thumb, 2. Now, is 2 networks enough? No, we need 6 in our case. So you put up another digit and you double that number, and that's 4. And I'm looking at my diagram here. We need 6 networks. 4 is not enough. So leaving these 2 digits up, we then double it again and go to 8. And then we think, hey, wait, is 8 enough? Is 8 networks enough? And the answer is, yes, it is. And you just look visually at your hand and say, how many bits do I have up? Remember bits? How many bits do I have up? It's 3. So the finger game is simply calculating how many bits do we need to take from the host portion in order to go ahead and actually do custom subnetting for a certain quantity of networks. That's all it is. So let's take a look at our topology, and let's do another scenario. Let's imagine we need 14 networks instead. So we've been given one major network. We've been told we need to create 14 networks. My question is, how many bits above and beyond the default or the standard mask here of 24 are we going to need to support 14 networks? And the game is this. When in doubt, you do the Fonzie move. Now, if you don't know who Fonzie is, I was born in 1964, so I grew up on Happy Days in the 70s. Anyway, Fonzie, hey, like, hey, how many bits do you need to steal? Hey, I think I can figure this out because there's a number on my thumb, a 2. And that's what you do. You start there. You start with your thumb up with a 2, and then you keep doubling it as you bring up additional bits. So let's go for 14 networks. How many bits is my question? How many bits would we need to steal to get 14 new subnets? And the answer is 1 bit is only 2. That's not enough. You double it, 4. That's not enough. You double it again, 8. That's not enough. You double it again, 16. 16 would work. I'm looking at my screen here. 16 would work. We only need 14 networks. So how many bits, my question to you right now, is how many bits would we need to steal above and beyond what the mask we were given was to create at least 14 new networks, and a total of 16 actually. If you're looking at my fingers and saying, well, Keith, if your fingers represent bits, there's 4. And so as you bring up your fingers, you don't have to count your fingers. As you do that, you just keep doubling. Let's do one more. Let's imagine that we need 66 new networks. So we've been given a design and we've been asked to create 66 new subnets. And we realize that, well, if we only have one network to start with, like Elm Street, that's huge, we need to carve it up into a lot smaller networks and subnetworks. And to do that, we are going to start borrowing or stealing what used to be host bits and use them for subnetwork bits going forward. So if we need 66, my question is, how many bits does it take to get 66 subnets? If you're not sure, which many people aren't, like you, how would a person just know that off the top of their head? You put up your thumb. It's got a 2 on it. And this time, I'm going to focus on just doubling the number every time and not focus on how many digits, because I can just look at the end and say, oh, I have this many fingers up. All right, so let's start. We're going for 66. 2 is not enough. 4, 8, 16, 32, 64. Not quite enough. We're going for 66. So 64 times 2 is 128. So that is 7 bits. 7 bits is what we would use to go ahead and create that many networks, which isn't going to leave a lot for host bits. We'll talk about that later. But that's the calculation of what we would do to identify how many bits we would use to create new subnets. Let's do one more. Let me go ahead and clear off this screen. And with that cleared off, let's imagine that we've been given the network 172.16.0.0 with a, let's actually change that. I'm going to make it a little more interesting for both of us. 16. Let's make it 128.0/ and we'll make that a 17-bit mask. Great. And they say, this is your starting point. What? Okay, so this is the network that we've been given from our boss or the powers that be. And they've said, well, make all this work. And we need 6 networks here. So we need six networks from this parent network address space. So my question for you is, starting with the 17-bit mask, how many more bits would we need to use to actually create 6 new networks? And if you might be thinking, Keith, you sneaky dog, this is like the same exact question we had at the beginning. And you're right. 6 networks is 6 networks. It doesn't matter what the starting point is as far as the mask is concerned. The question is, how many more bits do we need to actually use to create new custom subnets? So if we need to create 6 new subnets, we would get our thumbs up and say, well, 1 bit is not enough. That's only 2, because there's a 2 on your thumb. Starting point for the finger game. Start with a 2, and then 4, then double again, 8, and that's enough. So we can create 8 new subnets with, and just look at your fingers, 3 bits. So here's how we could apply that. Check this out. We'd say, well, 3 more bits is what we're going to use. So my question for you is, if we have this mask of /17 plus 3 more bits, and let's do the high math together, what would the new mask be? And some people might say, well, Keith, see here, 17 plus 3 on a good day is 20. And that would be indeed the new mask. So you take this network of 172.16.128.0 and you simply slap on a 20-bit mask. So a 20-bit mask in binary would look like this. Let's do it in decimal, dotted decimal. 255 means the first 8 bits, that's 8. And I'll put that in parentheses. Plus, and then we have 8 more would be 16, so 255, that's 8 more, 16, plus 4 more. Oh no. So we would just break this down if we needed to. 2, 4, 8, 16, 32, 64, 128. And as you work with these more, you'll be able to do these in your mind without actually writing them out, but I'm doing it for the benefit of everybody who's joining me in Subnet Saturdays because I don't want to leave a single person behind. So if we needed to figure out this octet in dotted decimal for the mask, I'll label that too for the mask. It is, there's 16, and we need 4 more for 20. So 17, 18, 19, 20. Then we draw in a line right there. And this part is network, says the mask. And this part are host bits, say the mask, because that's the dividing line. And these would be zeros. So our mask would be 255, 255, and then this first 4 bits on in the mask would be 128 plus 64 plus 32 plus 16. We've had videos on that of how to convert from binary to decimal, and that equals a whopping 240. So that's 128 plus 64 plus 32 plus 16. And that's the 3rd octet. And then for the 4th octet, it would be a 0. So a /20 in dotted decimal would be 255, 255, 240.0. Yep. You know what? I want to show you guys one more thing. I was going to hold this back until our next session, but I can't help myself. Last session, last live stream, we talked about the block size. And the block size is the least significant bit of the mask that's on. And this is how you can apply this and make your life so much easier. Check this out. If we look at the least significant bit of the mask, which is in this 3rd octet right here, I'm going to go ahead and put that in a nice blue color right there. So here's the least significant bit in the mask that's on at 16. With this new mask, if we're doing custom subnetting, this is your first subnet. So the first subnet, it kind of looks like the original network, like 172.16, 128. I mean, it looks identical, but it has a longer mask. And then check this out, the second subnet, you take the block size and you, I still get chills when I think about this. You just add the block size to that 3rd octet, and that's your next subnet. And then you add the block size again and again and again, and that's going to show you all the literal subnets of that you're creating. Check it out. So in this 3rd octet, which is where the mask ends, we basically take the block size of 16, and the next subnet is 172.16 dot, and we take 128 plus 16. And I'm going to do the long math here. So we take the 3rd octet of 128 plus the block size, and that would be 4 there, carry the 1, and that would be 4, and that would be 1. I'm just going to check my math here. 8 plus 6 is 14, yep. 2, 3, 4, yep. 1, yep. So the next subnet would be plus 16 more, the block size. I'm going to put a square there for block. It would be 144.0/20. And wait for it, wait for it. The next subnet is literally going to be 16 more. It's just the block size again and again and again. Let's take a look. So if we take 144 plus 16, that's going to be our next block size. So 6 plus 4 is 10, 0. We'll carry the 1. That would be 4, 5, 6, 160. So our next subnet would be 160 in that octet. So that'd be dot, 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 and that'd be 0/20. So I want to give you an application for that, but my main focus for this video and this live stream was to identify primarily, and we'll cover more detail on the subnetting, was to primarily identify how many bits. When you ask, or when you're given a scenario where you're trying to think, okay, I need to do custom subnetting, it's always going to mean that we're taking bits that were normally, the mask ended and the host bits were all available for host addressing, but when we do custom subnetting, we are stealing some of those bits and using them for the network. So the mask is going to grow. So does the mask need to grow by 2 bits or 3 bits or 4 bits or 5 bits or 6 bits? It depends on how many new subnets that you want to create. And so if we needed 12 subnets, let's do this together. You need 12 new subnets. How many bits do you need to steal? How many more bits than what you were given do you need for 12 subnets? 2 isn't enough. 4, 8, 16, that's enough. 4 bits. So what I do when I do this, I'm not counting how many fingers are up because I'm just focusing on doubling. I start with a 2 because it's on my thumb. I start with a 2, and I simply start doubling it as I bring up fingers. And once I reach or exceed the number I need, I stop. So let's do one more. Let's say we need 120 subnets. This is going to be a two-hander. We need 120 subnets. How many bits does it take to get to 120 subnets? Let's figure it out. That's not enough. 2, 4, 8, 16, 32, 64, 128. That's enough. I mean, we can do 128 subnets, and that's 7 bits. I'm just looking at my hands. That's 7 bits. So I'd take whatever the mask was, extend it by 7 bits, and then the next step would be to take that block size of that new mask and simply add it and add it and add it to identify your individual subnets. Pretty fun. So that's the key point I wanted to make today, but I thought maybe we should reinforce some of this with a little live interface action as well to help bring it home. So let's take, I need to jot the screen down, otherwise I'm going to have a problem remembering. Let's take the 172.16.128.0 network with a /20, and the next subnet is 144 as I jot this down on a separate piece of paper, and 160. And let's actually put those on a router. And that would help us demonstrate that that they're actually separate networks from each other. And the mask is 240 in the third octet. Great. All right, and that'll help reinforce. So here's what we'll do. We'll take these 3 networks, the 172.16.128.0 with the /20, which is this mask in dotted decimal. And we can't actually, so this actually represents the network itself. And so the challenge is you have to have a host address that has at least 1 bit on in the host bits. So let's create some interfaces, or let's actually go configure these interfaces on router 1. And it's got 3, that'll do. And let's go ahead and give router 1 the IP address of .1 in the last octet for each of these. So router 1 will be .1, .1, .1. And when we put those IP addresses in and we do a show IP route, this router is going to believe that he is directly connected to the 172.16.128 network, the 172.16.144 network, and the 172.16.160 network. Now, a couple things. Let me bring that up real quick. That's what I hope happens. Now, if I got my math somewhere wrong here because I was rushing it or whatever, I'm going to totally ditch this live stream and we'll redo it again. But I think the math all looks solid. I did it longhand. I think it looks like what it should be. All right, let's go to the interface and check this out. So I'm going to hide that off for just a moment, and let's bring up, I think I've got a router that'll cooperate. Maybe this one will. So this is router 1 from our topology. It's got some interfaces, and it's got some routing protocols running. All right, so I'd like to share with you a couple of things that I do occasionally that really help speed things along. One is, if I do a show, before I start configuring, I want to see what's on this router. Make sure I'm on the right device. So let's do a show IP interface brief like that. And okay, so there's gig 0010, and I'm looking down at my notes here, and 20. All right, let's take those in order. So on this interface, 00, let's go ahead and give it the first IP address in the 128 network. And then we'll do 10, give it the IP address in the 144 network. And we'll take the gig 20 and we'll put it in the 160 network based on our plan earlier. So with IP version 4 addresses on a Cisco router, if you put in a new IP address, it overwrites the old one unless you use the secondary keyword. But so we could either default these interfaces or just put in the new IP address, and that'd be fine. So I'm gonna do a show IP OSPF interface brief. Show. I'm in trouble here. All right, so I'm gonna take out OSPF because once we change our IP addresses, even if they're enabled in OSPF still because of a network statement, if 2 neighbors don't agree on the area that they're in or the actual IP subnet that they're connected to, they're like, I'm out of here. So the timers have to match, authentication have to match, the network has to match, the network type has to match, within range, within reason. So I'm going to just take off OSPF first so that we don't have these bouncing messages from neighbors dropping off as we continue our configuration with different IP addresses based on our plan. All right. So we'll just do a no router OSPF 1. That should do it. Boom, 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 bombs going off. All right, so we don't have to worry about those messages anymore. Let's go into interface gig, and it was gig 0/0 for our first subnet. So in interface configuration mode, we'll specify IP address, and the address we want to use is 172.16.120. Get my 128.1 with a 20-bit mask. And so there's 8 bits for the mask, 16-bit for the mask, and 240 is 4 more bits for the mask in the third octet, and the rest of that, the entire last octet is available for host addressing. So this is literally doing custom subnetting based on that parent network address space that we were given and worked with earlier. So I'll press enter, no errors, that's great. Let's go to interface gig, and the next interface as I lean down on my notes is gig 1/0, 1/0. And these are all up. They were up previously, so I don't need to bring them up. And we need IP address. So I'm gonna hit the up arrow key a couple times. And this time the IP address, instead of the third octet being a 128, that third octet is gonna be 144. And the last octet is gonna be .1, which is the host portion. Okay, and then we'll go to interface gig 2/0. And we'll use the up arrow key a couple times. And that third octet, instead of being on the subnetwork 144, we can refer to this one lovingly as the subnet 160. Just like that. So with those 3 IP addresses, if we did a do, because I'm in configuration mode, so I need to do a do so that I can do a show command, show IP route connected. This is just a way to look at your directly connected networks and not all the OSPF routes or anything else that might show up, although I killed OSPF. What this says is, hey, check it out. You are directly connected, says the router. I know how to reach the 172.16.128 network. That's our first subnet. And then I also know how to reach the 172.16.144 network with a 20-bit mask, my second subnet. And I also know how to reach the 172.16.160 network. So this is a little beyond what I'm hoping you'll be just like, oh, I got this down. My goal in this video was to reinforce the idea, just the concept, that if we have a mask and we want to do custom subnetting, we need to make the mask a little bit longer. How much longer? That's a quite good question. It depends on how many new subnets we want to make. And so the key takeaway from this video is that if you want to identify how many more bits, and then when the next video and the next live stream for CCNA Saturday, we'll start applying these concepts even more. But if we want to create custom subnetting, we first ask ourselves the question, how many subnets do I need to create? It really starts with a why. Like why do I want to start taking additional bits above and beyond the default mask that it was, or the standard mask that was given? The answer is you want to create custom subnets. So if we wanted to create, let's do 33. Let's imagine we were asked to create 33 new subnets. And all we have is our fingers to calculate how many bits to take above and beyond what we were given for the mask. So if we're going for 33, let's do it together. One last time. One last college try. That's not enough. That's only 2. I know because there's a 2 on my thumbnail. So some people are visual learners. Some people are auditory. Some people are more touchy-feely and kinesthetic. So whatever way you can remember that first thumb, like 2, 2, 2. Any way you want to do that, it's fine. So just remember, put your first bit up and say 2, and then keep doubling. You always double when you're doing the finger game. Start with 2 and double. So we're going for 33, so 2's not enough. 4, not enough. 8, 16, 32. Oh, so close. Maybe we don't need a voice VLAN. Yes, you do. So boom, 64. So if we want 33 subnets, we've got to take 6 bits above and beyond what we were given. And then we take that block size and simply take the first network and the new mask and just boom, 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 and calculate them out. So 6 bits would be required to support 33. We'd have extra room for extra subnets, but if you want to meet the requirement, that's how you do it. All right, I really enjoyed having you in live stream today. This will be a recording. I'll put it back up on, it'll be up on YouTube probably in a few hours. I'm going to clip off the beginning and the very end, because after we do some music here in a few moments, I'm going to stick around and we'll do Q&A. And that part doesn't get saved persistently on YouTube. I just clip that so it's just between us. So if you're in the live stream, which I'm grateful for, there's quite a few of us today, that's fantastic. So this next chat is just for us. And our next stream is tomorrow. And I have 2 or 3 ideas that I'd like to cover. They're all related to Cisco CCNA 200-301, and I will be posting that later today, what that topic will be. So if you have time tomorrow at 11 a.m. Pacific for CCNA Sunday, please join us, and I'll add that to the playlist as well. So again, if you haven't, I love what I do. I love teaching. I love Cisco. I'm an average learner, really. I mean, I right down the middle. I see people who can learn really, really fast. I'm like, wow, that's amazing. It's not me. I'm an average learner, super average. And so I'm creating these techniques and things for other people who I think are like me, that so you can get it, so you can get the parts of subnetting, how it works, and enjoy the journey. If you haven't already, please click on subscribe. If you like this video or found it useful, give it a thumbs up so others know, or leave a comment. That'd be great. And the master playlist for CCNA, I encourage everybody who's going through CCNA studies to give that a listen. Maybe schedule a few, like I'm going to watch 2 or 3 of those videos a day and just enjoy them together. And I'll be there every step of the way with you. So I'm going to do some closing music. Then we'll come back for some Q&A. And until then, I appreciate you watching, and I'll catch you next time. Thanks, everybody.